All right, so lecture 33. Yesterday was an interesting day. We learned a lot of scary stuff. Well, scary for you, not for me. Don't you want to get to that point? Don't mind me wearing a hat. It's cold down here in my basement. Does anybody have a particular question before we pick up with what we were doing yesterday? And I want to do some examples today. That's sort of where we're at. Okay. Any questions, comments? No? I'll check the chat, see if anybody's chatting up. No. Okay, so I have a homework for you guys. I didn't post it yet. I will do that this afternoon. But what I'd like you to do is pay attention to these examples because they're going to help you with it. So let's remind you of what we did yesterday. That was last class. We'll use a nice blue. So last class, we discussed two very important things. We discussed the divergence test and the integral test. So you need to know what those things are and how to use them. We also, and this is also important, we also showed that the harmonic series what was the harmonic series? It was 1 plus 1/2 plus, so there's 1 plus 1/2 plus a third plus a fourth plus a fifth for eternity. We showed this guy actually diverges. So that was a big class. Please check the, once I got to upload the whiteboards. I keep forgetting, I apologize. Once I get all that, you got to check that out. It's a very important problem. I would also encourage that you went to the internet and Googled the harmonic series and studied how it has applications in all sorts of places. It would be worth your time. Oh my God, they're cutting grass outside. You hear that? The mowers are a mowing. All right, so. Someone have a question? No. All right, cool. So let's do some particular examples. Let's get a different color here. So here's what you need to understand. The following diverge because of the divergence. So let's look at a couple series that we know just by looking at them that they can't converge. So let's take something like k goes from 1 to infinity of 2k over 7k plus 3. What is this equal to, by the way? This is 2/10 plus 4 over 15, right? I think, yeah, no, 2, 14, and 3, it's 17. Plus 6 over 24. This guy diverges. So why does it diverge? Well, if you take the terms and ask what happens to their limit as k goes to infinity, this limit is not 0. It's 2/7, which is not equal to 0. So a way to think about this is that if you're adding this, if you're trying to compute this series, essentially you're going to be adding 2/7 together forever and ever and ever and ever. Well, how the heck can you add 2/7 together and equal something? You can't. So that's one way to think about what's going wrong here. What's happening bad? What are the bad behavior? So let's call this example, we'll call this 1A. Does anybody have a question about this? Okay.
So as long as the divergence is not equal to 0, like the limit rather is not
Right.
equal
Well,
to
we're going to get to that. But divergence, it's going to diverge if that limit is non-zero. Absolutely 100% of the time. Now, the opposite is not true. It's possible, as we saw with the harmonic, for the limit to be 0 and it still diverge. That was the whole point of yesterday.
Yeah.
And it's not easy to learn that, and I would encourage you guys to spend the necessary time on that. Okay, so let's do one more of these creatures that is absolutely going to diverge. Let's take the sum of, how about, let's use a different letter. How about n over log of n? N goes from 2 to infinity. So what is this? This would be 2 divided by log 2 plus 3 divided by log 3 plus 4 over log 4. Can this guy converge or diverge? Well, we know it diverges. Why? Why does this guy diverge? Well, again, we look at the limit. Let's look at the limit as n goes to infinity of n over log n. How do we compute this limit? Well, this limit, if I just plug n equal to infinity, I have to use L'Hopital's rule because I get this thing called an indeterminate. You might remember L'Hopital's rule from way back in Calc 1. So L'Hopital says I can differentiate the numerator and I can differentiate the denominator and then take the limit. So this becomes 1 over n, which is the limit as n goes to infinity of n, which is clearly infinite. So these terms are getting bigger and bigger. So there's no way that this thing is going to add up to some finite number. So does anybody have a question about this as you stare at the moon or the earth behind me? Such a beautiful thing. Okay. If you don't have questions, then I move on. So again, I am giving, these were two examples that diverge because of the divergence test. Now let's look at the next type of example. I'm going to switch this. So this is example 2. These guys, nothing can be determined by the divergence test. So let's look at an example of that. So let's take this guy, 1 over k squared. So this guy, which is 1 plus 1/4 plus 1/9 plus 1/16, this guy may or may not converge. Why? Because we have this limit. If we look at the terms, they actually go to 0. So the divergence test says if you go to 0, you may or may not. We have to investigate further. So I guess this should say nothing can be determined. Okay, so the divergence test is really only useful when it tells us we get divergence. When we have this limit going to 0, it tells us nothing. We need to use more information. So I tried to get your attention to this when I talked about the divergence test yesterday. I said you really need to understand the logic of the statement. And it's not easy to do that. It takes a lot of critical thinking. Okay, let's do one more example of something that we might need to study further. Let's use J for an index now, because why not? So the sine of J over J, and this thing would be the sine of 1 over 1 plus the sine evaluated at 2 over 2, etc. This guy may or may not converge. Since the limit as J goes to infinity of the jth term, this guy equals 0. If you're interested in why, it's our old friend, it's the squeeze theorem. So what these last two examples mean is these last two examples tell us that we need more tests. If you have a question, please let me know.
Is this where we'll eventually use the integral test?
Well, yeah, that's what we used yesterday. Yep. Well, amongst other tests. So we need more tests, which I like to call tools. Okay, so we had more tests. Yesterday we stated the integral test. But let's do some examples. With the integral test. So let's take one. So let's take the series that we started before. Let's say k equals 1 to infinity, 1 over k squared, which of course is 1 plus 1/4 plus 1/9, etc. So does this converge? Well, the answer is yes. So in the previous problem, we said that the divergence test didn't give us any info. Didn't give us anything. Nada. But if we use the integral test, we can get information. So we studied improper integrals. And we know the following. So what do we need to study? We need to study the integral that corresponds. So we need to study this guy, the integral from 1 to infinity of 1 over x squared dx. Now we know that this guy converges. Now you should convince yourself if you don't remember. So hence, we conclude this series converges. Now, a couple things that are important. We're not saying anything about the value of the limit. We're not saying anything about the series' sum. We're not saying it equals something. You know, when we did geometric series, we could tell you what its sum to, what the limit was. We can't do this here. We can't. Does anybody have a question about this? Okay. All right, so then this is a very important result. So the second example, and this is very important, these are called P-series. So now we're going to give you a specific type of series. So if P is greater than 1, then 1 over k to the power P, k goes from 1 to infinity. Why? Because if P is greater than 1, this integral converges. We actually did this together a few lectures ago. We actually showed you that if P is greater than 1, this integral converges. So the P-series are a very, very important class of series. You should know them. We're going to use them a ton moving forward. Does anybody have a question? Now, look, this is a scary thing, but these P-series show up lots and lots of places, and you guys will, oh boy. So let's write down a couple important facts. So for example, this guy, 1 over k to the third power converges. What is this guy? This is 1 plus, when k is 2, you get 1/8. When k is 3, you get 1/27. K is 4, you get 1 over 81. This guy converges. 1 over, let's say, K to the 10th. This would be 1 plus 1 over 2 to the 10th, plus 1 over 3 to the 10th, plus 1 over 4 to the 10th. This guy, these guys both converge. So here, it's nice to know what your P is. Here, your P equals 3. That's clearly greater than 1. And here, your P equals 10, which is clearly, excuse me, that is also greater than 1. What is happening? Stick. For comparison with that, and this is important, if P is less than 1 or equal to 1, this guy diverges. So if you have a question, let me know. Going once, going twice. Okay, so let's do another example of the integral test. So this would be the third example. So let's take K goes from 1 to infinity of K over K squared plus 1. Will this guy converge? Let's remind ourselves what this is. This is going to be 1/2. And then when K is 2, you get 2 over 5. And then when K is 3, you get 3 over 10. So we want to know, does this converge? This guy will converge. And to see why, what we want to do is we want to use the integral test. So this means we have to integrate the corresponding function. What is the function? It's going to be x over x squared plus 1 dx, and this is from 1 to infinity. Now, let's be very careful with how we do this. We remember that these integrals require we take a limit. So I'm going to take the limit as b goes to infinity of this thing. Okay, now, how do I integrate this? Well, this guy is going to require a substitution. So some of us can maybe do this mentally. Most of us need to write it down. So what's the substitution? Well, I am going to set u equal to the denominator. So let's come over here in blue. So I'm going to use u equals x squared plus 1. So that means my du is 2x dx. So when I do this, this integral becomes 1/2 1 over u du. Okay, now, what are the bounds here? Well, the bounds, if x is 1, the bound here is 2. And then if this is b, this is b squared plus 1. And so if we write this out, this is 1/2 this limit. Now, what's this integral? This becomes the log of u evaluated from 1, or excuse me, from 2 to b squared plus 1. Which is 1/2 this limit. Now, this limit is infinity. The log goes off to infinity. So what does that mean? Well, that means if we go back, oh, excuse me, this is not converge, it's diverge. This means because the integral diverges, that tells us the series diverges. So does anybody have a question about this?
Yeah, how did you get the bounds again?
How did I get them?
Yeah.
Well, replace x. So if you look over here in the blue, when x is 1, what is u? Well, what's 1 squared plus 1? It's 2.
Okay.
And when x is b, you get u is b squared plus 1.
Okay. All right. I see what you did now. Okay. Never mind.
No, that's a good question. Okay. Sweet. So that's there, the integral test. Fun times. Okay, so does anybody have a question about this? Okay, so we'll give you some practice problems with that. It turns out, though, we're going to do some more tests right now, and it turns out a lot of times the integral test can be avoided in lieu of some other test. And sometimes that's a good thing, because if we can ignore integration, especially these improper integrals, that is often a good thing. So that's what we want to do now. We want to turn our attention to another test. So let's do that. In honor of another test, let's change the background, because I'm bored with this background. And what else are we going to do to enjoy life than to change our backgrounds? We already did the other ones and I deleted them. So let's go none. Now you can look at the playroom that the kids hang out in. All right. Fun times. Happy Friday, pilgrims. All right. So our next topic is the next test. So our next test And I would say it's very intuitive, but you're going to say it ain't intuitive. So it is called the comparison test. This is what we do all the time in math and science. When we want to learn about something new, we compare it to something old that we already understand. That's what we do. So it's a very logical and sound thing to ponder. So that's what we're going to do. Now imagine this. Imagine if you have two things you're comparing, and here's the idea. So here's the idea. Assume we have the following sort of assumption. Assume that 0 is less than or equal to a sub 1, and that's less than or equal to b sub 1. Let's assume a sub 2 is always less than or equal to b sub 2. So in general, let's assume that the kth term in A, my kid is, what is she doing up there? Ricky! So look, we're basically saying I have two lists of numbers. I have A's and then I have B's. And then there's some order. Like A1 is always less than B1. A2 is less than B2. So in general, the kth A is always less than the kth B. Okay, so what does that mean? Well, yeah, we want to come paint. That's what we want to do, paint. Okay, so what does it seem reasonable to expect? Well, it seems reasonable to expect that if I add up a sub 1 plus a sub 2 plus a sub 3, if I decide to add this up to some number a sub n, we expect that this would be less than this. You guys are all right. Ricky, do you want to come say hi? Yes, hon. Hold on.
We're going to go paint. Yes.
You're going to go paint? You got your shoes on. You want to come say hi? You want to show everybody your cast?
Yeah.
Come here. Come here. Although we don't know. They might all be sleeping. Show everybody pink. Show them your cast. Don't touch that. No, no, no. You broke it last night. Say hi. Ricky, look. Who's that? Okay.
Aww, little O'Grady.
Show them. This is one of the little demons. All right, go get your shoes on and get changed, Ricky.
All right, come on.
You got to go bye-bye. You guys leaving. All right. See, that was fun, guys. Daryl, you're alive. I wonder who else is alive. No one else. Everybody else is in zombie mode.
I'm alive.
Are you?
Oh, look.
I am.
That's good. All right, bye, Ricky.
We're
Bye.
going up.
Bye. Say bye-bye.
Bye.
Yeah,
We're gonna go
okay,
paint.
okay, go paint. Have fun. All right, so again, if we're adding a group of numbers and if I correspond them, if A1's less than B1 and A2's less than B2, then it makes sense to expect this to happen. And so if we take the limit, what we expect is we expect 0 to be less than this guy. Let's use K because we were using. the subscript is K, and we expect the sums of the A's to be less than the sums of the B's. So again, when I wrote the A sub n up there, remember that is, we call that S, those are the partial sums. So if we take the limit of the partial sums, by definition, the limit of the partial sums is the series. And so we would expect that to be true. And so we can make the following conclusions, and it's very logically sound. Thus, if this guy converges, we know this guy converges. Alternatively, if we assume that A diverges, then the B's, series of the B's must diverge. And so that's why we call this the comparison test, because we're using one known series to get information about a unknown series. So let's write diverges again and spell it a little more clearly. So think about this. We already have some known series in our arsenal. We now have the P series. We have geometric series. We also have the divergence test. So we have a decent amount of series that we know whether they converge or whether they diverge. And then the general idea is now, okay, what if we come across a new series that we're not quite sure how it behaves? However, if we can compare it to one of those known guys, then we can get information. Makes sense, right? Of course not. You're like, what is he talking about? Some of you are like, all these letters and subscripts. I hate this. I feel for you guys. I do. But the platonic love comes through the computer and says, go learn this. You can do it. Okay. Does anybody have a question about this before we do some examples? You guys love examples. I know this. Examples, 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 examples. So let's do an example. Get to the 15th page. Let's change colors. This purple's getting on my nerves. Let's go blue. So oftentimes the way we'll state the problem is we'll say something like determine whether a series converges. So let's do this guy. Let's say 1 over k squared plus 10. So let's write out the first few terms for practice. This is 1 over 11 plus 1 over 14 plus 1 over 19, etc. So let's remind us that k goes from 1 to infinity. That's an ugly infinity. It's like got flattened by. Okay. How much fun are we having? Millions, I guess. Okay, so determine whether this thing converges. So what we're going to do is we're going to use the comparison test. And the reason I'm going to use the comparison test is the following. I am looking at this thing and I'm saying, okay, it looks sort of like 1 over k squared, but it's not. And I know that 1 over k squared does converge. So I am suspecting that this guy converges. So here's what we're going to do. So let's change colors. We'll go to this green. So let's use the comparison test. And what I want to do is compare with the known to converge series. Which series do I know converges? Well, I know 1 over k squared converges. This is a p series. I know it converges. We just talked about that 10 minutes ago. Okay, so here's the observation. What do? I need to do the following. So what I'm going to do is I'm going to set my a sub k equal to 1 over k squared plus 10. And I'm going to note that this is less than or equal to 1 over k squared. Again, we had this conversation. Last class, I believe, or maybe it was the class before on Tuesday. If you look at this inequality in the middle here, this is just basic numeracy skills. K squared plus 10 is always bigger than k squared, which means those fractions have to agree to this inequality. So by the comparison test, we have this. Hold on a second. This is ugly. So we have this, and hence convergence. Excuse me. So this is how you use the comparison test. You find a series that you can compare it to, but you can't just choose any old series. You have to have one that you either know converges or diverges. What's happening up there? All right, does anybody have a question about this?
So when you're testing for those convergences, are you usually going to use a p-series?
Oftentimes, yes, but not always. P-series, that's why I make special attention to the P-series, Jeff. It's almost, I mean, I don't want to say 100% of the time, but in a class like this, it's going to be 90% of the time you're going to use a P-series.
All right, good.
Not all the time, but very often. I don't know. Does that make sense? Again,
no, it does. I mean, I'm just better than 10%. I'll probably have a question about, but you know,
that's all right. No, it might not even be 10%, dude. It might be less than that. Yeah, it's almost certainly going to be a P series, and the reason, I mean, it could also be a geometric series too, but it's usually a P series. And what you'll start to notice is that there's a theme to these. So like if you read this section in the book on the comparison test and you start doing examples, you're like, oh boy, okay, I see where this is going. So let's do another example and maybe it'll be a little more clear. Let's do another one. now my kid's crying. So let's look at this series. So let's take the sine of, say, 3k over k to the 5th plus 7. So here k goes from 1 to infinity. And so we can ask, does this converge? So the theme that I would encourage you, if this goes off the sort of tails off your question, piggybacks off it. Anytime you see index to a power, you should be thinking p-series. Now, it's not always the case, but anytime, what I mean by index to the power is I see k to the 5th. That is sort of like someone standing there flashing lights and screaming, p-series, p-series, compare, compare, compare. So you start to pick up on these themes, and what you want to do is you want to try to take advantage of them as best you can. And so note, if I want to solve this, I can say, okay, the sine of 3k, let's do some very, I don't want to say, I don't want to say easy, but let's make some deductions. Let's note that this thing always, 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 what do we know about the sine? I don't care what I can plug into sine. The largest it ever is 1. So I can replace sine with 1. So if we're looking for some reasoning here, what is my rationale for this particular thing? Don't ever forget that -1 is less than or equal to sine x less than or equal to 1. So I'm using that fact right here. Okay, then the next piece of reasoning I'm going to use is the same reasoning I used in the previous problem. This is always going to be less than or equal to just k to the 5th. So I'm not saying this is easy, but if you spend some time thinking about these inequalities, you'll start to see that they're very, very natural and intuitive. Don't worry about the letters and numbers. Just pick specific values of k. Convince yourself that these inequalities hold. And so how can we finish this problem? Well, we can say the following. So we conclude this guy converges. What is happening? Is my wife killing my kid? So what we would say is we can conclude this guy converges with comparison. And what are we comparing it to? We're comparing it to with the convergent p-series. And what is the value p here? The value here is p5. So that is one way to write up a problem like this. When you're studying series, you always want to do two things. You always want to state whether it converges or diverges. And most importantly, no one cares that you can flip a coin and guess. What we want you to do is that you can explain what logical reason, and that means what test gives us convergence or what test gives us divergence. I hope that makes sense. Does anybody have a question about this?
Can you go back to the slide right before this for 1 second?
I can. Yes, ma'am. This one?
Yeah, thank you.
Yep. If anybody has a question, please let me know. Oh my God, the calming has happened upstairs. Any questions about this? comments, concerns?
I have a
Okay.
question.
Yes,
So with our result, we'll always write it out as a sentence to end it?
I would, yes. I mean, if you're asking me my preference, I think you should always write things in sentences. That's just my prerogative. That's how I feel like it should be done. Other instructors might not care. They might just, you know. Look, it depends too. You guys know how I give exams. I'm not going to give you an exam where I say true or false, converge or diverge, or I'm not going to give you multiple choice. So if I give you a problem, and you'll see this on the next homework, I'm going to say state with proof whether it converges or diverges. And your job is to do two things. It's to figure out which test to use and then tell me how that test applies. So I'm leaving lots of room. There's many ways that you could write this up, and I could say that's a very good solution. But it's hard for me to comment on your question until I see how you would submit your homework. Does that make any sense? So yeah. So I mean, I guess you could just say, you know, you kind of always want to use sentences, because even when, I mean, notice like I'm using periods. You know, even if you look at this screen, I'm saying note, and then I'm writing a sentence. You know, when you read those inequalities, that's a sentence. And then you'll notice that I finish with a sentence. Now, you could come up with better ways of writing it so that you don't have to keep repeating yourself. Like you could just say, you could say in the beginning, say you've done your scratch work and you know it converges. You could say it converges. You know, another way of writing this solution that would save space is you could say this converges by comparison with the series 1 over k to the 5th. And then you'd be done. Does that make sense? I don't know if it does. Again, you'll get, once we do some more of these, you'll start to see how I write them up and how I think that is best for not just me to do it, but also you guys as learners. Any other questions? Going once, going twice. Okay, well, if you don't have questions, I will end the recording right after I save the whiteboards. All right, so I'm going to end the recording now, and I will see you guys on Tuesday. Have a good